Okay, so think of a rock spinning on a string, right? And that rock is pulling that string taut. Could we use system rotation as a design element in order to solve our long, skinny wing problem? So rather than one aircraft that can't do the job on its own, imagine we had multiple aircraft that are tethered together in a hub and spoke arrangement spinning, but the sole purpose is to put those wings under tension.
You're listening to the Drone Radio Show podcast, the show about drones and the people who use them for business, fun, and research. Hosted by Randy Goers.
Hello, everyone. This is Randy Goers, and welcome to the Drone Radio Show podcast, episode 454. How close are we to achieving truly persistent flight in the stratosphere? And what would it mean if we could? For that question, we head to Hampton, Virginia, to speak with Justin Selfridge from Devorto Corporation. Devorto is developing a breakthrough high-altitude platform called the Tethered Uni-Rotor Network, or TURN, a completely new aircraft architecture designed to combine the vertical lift and loitering capability of a helicopter with the aerodynamic efficiency of an airplane, enabling long-duration, solar-powered flight in the stratosphere. Justin is the founder and chief executive officer of Devorto, where he leads the development of this next-generation persistent drone technology. Backed by both private investment and government support from organizations like NASA, the U.S. Air Force, and the U.S. Space Force, Justin and his team are working to redefine how we think about high-altitude operations, with the potential to disrupt both satellite and traditional aerial platform markets. In this episode of the Drone Radio Show, Justin talks about why the stratosphere is such a critical domain for future aviation systems, how the TURN platform works and what makes it different from anything we've seen before, and the real-world applications and impact this technology could have across commercial and defense sectors. But before we hear from Melissa, I want to say that your support is the heartbeat of this podcast. Every episode is created with you in mind, and your generous donations help cover production costs and keep the show going. Whether it's the price of a cup of coffee or a larger contribution, every bit helps to donate. Visit droneradioshow.com/donate. And if you can, please subscribe to the podcast on your favorite platform and leave a review. It really helps the show stand out among the thousands of podcasts out there. If you have a great story about how drones are being used, I'd love to hear from you. You can reach me at randy@droneradioshow.com. So let's learn how persistent stratospheric flight is becoming a reality and what it could mean for the future of aerospace, with Justin Selfridge of Devorto. Let's pick up the interview where I asked Justin to introduce himself.
Hi, everybody. My name's Dr. Justin Selfridge. Before this, I worked at NASA Langley doing adaptive controls for experimental aircraft, came up with a new novel aircraft design, pursued my PhD on it, and have been funding the technology and the business through non-dilutive grants through the government.
Justin, tell us about Devorto. What does the company do?
So Devorto is building an aircraft that never has to land. So a solar-powered system that can collect enough energy during the day, can run on batteries at night. We're not constrained by how much fuel you can carry like a normal aircraft. We just want to persist indefinitely in the stratosphere. So we're not trying to get people or cargo from point A to point B. We just want that black box sensor package to live indefinitely in the stratosphere, so that way we can provide better capabilities in satellites, but for the cost and logistics of operating the drone.
What makes your technology stand out in this emerging field?
Yeah, I would say the desire to get to the stratosphere is nothing new. We've seen DARPA spending $750 million on both fixed wing and airships. Tier 1 aerospace companies have been pursuing this. Even Google and Facebook have been investing in early stage pre-revenue companies because they want those cell towers in the sky so they can actually grow the internet. The main hiccup is solar doesn't collect a lot of energy and battery doesn't store a lot of energy. So you need an extremely aerodynamically efficient aircraft in order to be able to solve this problem. And most of the groups that have been tackling this have just been looking at it through a fixed wing lens, right? Can we take a design that's already been around for 100 years and just push the envelope a little bit and see if we can get this to work? And unfortunately, with that design, solar isn't there, battery isn't there, and most of the mass just goes into the wing itself as opposed to the battery mass, which is where you really want it.
Before we get into the technology, help us understand the environment. What exactly is the stratosphere in terms of altitude, and why do we want to operate there?
Yeah, the stratosphere is really nice because it is 12 miles up. It gives us advantages over both terrestrial cell towers and satellites that are in orbit. So if you think about cell towers, they typically only cover about 3 miles of range. So you kind of have that limited range to be able to get cell phones connected. The other thing that a lot of telecommunications companies are having a problem with is it costs $80,000 per mile to connect those cell towers together. So if you're talking like really rural, remote areas, it doesn't make sense to put up that infrastructure where you just don't really have that low population density. On the other end of the spectrum, we have satellites, but even the closest ones are orbiting around 600 miles. So what happens is you end up getting really good one-way communication. So that's where things like GPS come into play. They're just beaming down a signal, but it's really just too far to do really good two-way communication. And so 12 miles up is kind of that nice middle ground where we're still close enough to be able to connect 5G devices with cell phone tower in the sky, but we don't have all the logistical nightmares of operating an entire satellite constellation.
Today, what do customers use to reach or operate in the stratosphere?
Yeah, I would say the biggest hiccup with a lot of the traditional architectures are the only thing that really goes routinely up to the stratosphere these days would be something like weather balloons. The main problem you have with the traditional weather balloons is that they're just kind of an up and down mission. You launch it maybe once a day, you get 10 or 20 minutes, and then it comes down. So, fine, that's great for weather. Google was looking at Loon, where they were trying to take weather balloons and ride the winds at different altitudes. And they could get some endurance of about 30 days, was pretty typical, but you're still based on wind. So eventually it blows the balloons a little bit towards the equator or perhaps into some countries that you don't want to be in. And just the deployment was just a logistical nightmare. Again, DARPA was looking at airships. You would immediately think that, oh, those can just loiter. So you don't have to have any power to just float. But what they found is that because the blimps were so large, any sort of wind that knocked it off course, they would be using all of their power just to overcome that wind. And it didn't represent a feasible solution. Aside from those, then everything else is really just looking at fixed wing designs. So when it comes to fixed wing, if you think about what goes into a low power aircraft, an aerodynamically efficient aircraft, imagine something like a glider, right? It really has that characteristic high aspect ratio wing, that long, skinny wing. Because if you're going to fly slow and try to reduce your drag, getting that high aspect ratio is the most significant thing to reduce that drag. And so all these groups have been pushing that design further and further and further and further. And then you end up with a spaghetti wing. The whole thing is just too flexible. And then your entire mass is going into reinforcing that flimsy structure.
Let's talk about the Tethered Uni-Rotor Network, or TURN. When I first saw it, I'll be honest, I couldn't quite figure out how it worked. Can you walk us through it and describe it as clearly as possible for our listeners?
Yeah, absolutely. I know for this particular aircraft, since it is pretty much unlike anything that most people have seen, a picture is worth 1,000 words here. But hopefully I've gotten pretty good at describing why it looks the way it does, and then everything else really kind of makes sense. So we just talked about gliders and needing that high aspect ratio wing, and it's becoming too flexible. So let's turn our attention to a different aircraft. Okay, think of a helicopter. They have long, skinny rotors, which actually droop under their own weight while sitting on the tarmac, right? It's only once the helicopter starts spinning that those rotors become very rigid, very stiff, because it's starting to spin and pull itself taut. So That's where the analogy ends because helicopters have terrible, terrible, terrible aerodynamics, right? They have to spin really fast. There's a lot of turbulence. But the question that I asked for my dissertation was, could we borrow the physics of a helicopter? Okay, so think of a rock spinning on a string, right? And that rock is pulling that string taut. Could we use system rotation as a design element in order to solve our long, skinny wing problem? Okay, so now here's where we got to use the imagination. So rather than one aircraft that can't do the job on its own, imagine we had multiple aircraft that are tethered together in a hub and spoke arrangement, spinning like the rotor on a helicopter, but with no helicopter body. But the sole purpose is to put those wings under tension. So now that we kind of have the why as to like what are we trying to accomplish, the big picture design of what the aircraft looks like. Some people prefer a helicopter analogy, where I say, okay, imagine a helicopter, get rid of the helicopter body, and then make the rotors, the 80% of it just be tethers. Okay, so that's one way to look at it. For my airplane background, I like to think of it as we just took one aircraft and paired it up with some of its buddies, and we're using tethers so it spins in a circle.
The ends of the rotors appear to have their own motors. How many motors are on the system, and how are they configured?
Yeah, so we always kind of gravitate towards 3 or 4 rotors, just depending on whether we want redundancy or what the payload looks like. But yeah, absolutely. It's each individual rotor can be thought of as its own little independent flying aircraft. So it has a wing, it has a fuselage, it has a propeller, it has a tail, and each of those independent aircraft rotor wings is responsible for its own local trajectory. And then it talks to a completely passive central hub, which houses the payload or the sensor. And then the central hub is coordinating all the maneuvers of each individual rotor. So it basically operates very similar to if you look at the central hub, it operates much like a helicopter. So it's thinking about things in terms of cyclic and collective. When you move out to each individual rotor, each of those avionics thinks more like a fixed wing aircraft, articulating pitch and stabilization.
How does the system generate lift?
Yeah, so when I describe rotor, kind of what I'm describing is the aircraft component, right? So if you were to strip away the whole system and just look at a air quotes rotor, then it behaves very much like a regular aircraft. So the propeller is driving it forward. That's what's inducing the system rotation. And then each of those wings is generating lift for the whole system.
Can you walk us through the power system and how you achieve persistent flight?
Yeah, so since the tethers are not transmitting data or power, it's literally just a best way to describe it is like a fishing line. Like we're just using it to induce system rotation. So each of the rotors or each of the wings or each of the individual aircraft is sized very much that you would a traditional aircraft. So each one has its own battery. Each wing is fitted with solar cells, and then that's sized appropriately to know that over the daylight hours, it's able to collect enough energy to put in the battery such that the motor can run on a 24-hour cycle. And then the idea is that during each day, you recharge the batteries. Overnight, you're using the batteries, and we just keep repeating that cycle.
How large is the system? What's the overall width of the aircraft?
Do like to put this in perspective because some of the numbers can get pretty large. So let me at least start with what some other aircraft look like. While at NASA, I had the opportunity to actually do some aeroelastic analysis for the AeroVironment Helios. That was a football field span wingspan, literally 100 yards, 300 feet. We're talking about the stratosphere, thin air. We need really, really big wings. Okay, so that's kind of the scale for HAPS in general. The largest wing that we looked at for turn actually was funded by a NASA grant, which would hold a 250-pound payload, drawing 1,300 watts of power. That wingspan was about 30 meters. So roughly about a third of what the AeroVironment Helios was.
How does the system take off?
I get that question a lot. So of course with tethers, it's like, oh, how do you deploy this thing? Does it need to drop out of like a back of an airplane or something like that? The solution is actually really simple. We have a retracting mechanism. So when we start on the tarmac, there are no tethers. So you can think of each of the rotors as just butting right up against the central hub. And then it just does a normal taxi. So with a regular airplane, you would do a taxi linearly and then take off. This just does a circular taxi like a rotor helicopter. And then once you get above your local obstructions, once you get past any sort of higher winds in the jet stream, once you're ready to really achieve that aerodynamic efficiency, that's when you let the tethers out and then you hit your aerodynamic efficiency.
So it goes up on its own, and when it gets to the appropriate altitude, the rotors kick in. Is that when the tethers start coming out?
Yeah, the motors are always providing thrust to be able to have the system spin. It's just for takeoff and landing, it begins in a much more compact form factor. And then the tethers extend. So now we can get that clean laminar flow, kind of move away from the traditional helicopter dynamics. And actually, for the benefit of the viewers, I do like to mention sometimes people hear the word tether and they immediately think like the drones that have that umbilical cord which comes down to the ground, like, oh, we can stay up because it transmits power from the ground. No, we are using tethers just to induce system rotation. We are a free flying aircraft. If we wanted to take off in Los Angeles, then we could navigate all the way over and provide broadband telecom connectivity in New York.
What were some of the biggest engineering challenges in developing the system?
Oh, yeah, absolutely. I would say from the earliest days, just because it's such a unique architecture, the very first thing that we did with a NASA feasibility study was just, is it even worth pursuing? Because if it's not going to provide any aerodynamic benefit, then, why go through the trouble? We were able to show that 250-pound payload, 1,300-watt power would be able to persist up to a 60-degree latitude year round. And let me kind of dive in as to why that's meaningful. Right now, the world record holder for solar powered persistent flight is Airbus Zephyr. Carries about 5-10 kilogram payload. But the kind of sweep under the rug is that all of the demonstrations are done in New Mexico during the summer, right? So you've got 16 hours of daylight and the sun is directly overhead. So if you want to consider a high altitude platform station that is complementing or replacing satellites, you have to think about being able to service Canada, the United Kingdom, the southern tip of South America. These latitudes, which are really far away from the equator, during the winter, they might only get 8 or 9 hours of daylight, and the sun is not directly overhead. So just where you operate could be 15 times harder than what's been demonstrated in New Mexico during the summer. So the first challenge that we really had to showcase was, could we get a large, meaningful payload up to 60 degrees latitude year round? Beyond that, everything was very much I'll call it the brains of the system. So if you can imagine, we have 3 or 4 independent flying aircraft, which are all tethered together, experiencing their own forces, their own interactions. And we're trying to control a completely passive central hub, which has no controls of its own. So luckily, my background is in controls. My faculty advisor said, your degree is in controls and not aerospace engineering. I said, look at this thing. It is a controls problem. And then some other things we'd actually uncovered over time. This is kind of interesting. Most people think that, oh, you just buy an avionics and you get roll, pitch, yaw. That's true, but there's more to the story. What you're buying is an accelerometer, a gyroscope, and a magnetometer. And then that goes into an algorithm, which gives you roll, pitch, and yaw. When you have something that is constantly spinning, the accelerometer can't tell the difference between gravity and radial acceleration, which really messes up those algorithms. So we found that we had to come up with custom state algorithms just to be able to have the system know how it's positioned in space and then be able to implement the control architecture from the dissertation. So definitely some interesting research problems have been solved.
What is the current status of the platform today?
Yeah, we are at a very nice inflection point. So I'd say the past few years, it has been addressing just the pure basic research of a brand new aerial platform. What is it going to take to get off the ground? We mentioned the state estimation and the controls and, kind of the dynamics of how all of these things interact together. Now we are at the point where we have an outdoor flying demonstrator. We are currently working under a $1.9 million grant funded by Space Force to be able to take that up to higher altitudes. And so the way I like to say is the inflection point that we're at is moving out of pure R&D and just more into development and really setting our sights on commercialization.
How does geography factor in? For example, how far north can the system operate?
All of Europe, about half of Canada, and southern tip of South America.
As you move into the next phase of development, what do you see as the major use cases? Who are the likely customers, and what will they use the system for?
Yeah, absolutely. The big one that the main market, the push, I would say would be communication, certainly. I mean, we've seen Google and Facebook investing in this because they want that telecommunications play. They recognize 70% of the planet doesn't have good mobile connectivity. So that's certainly just the tip of the iceberg, I would say. Earth observation is another big one. So if you think about operating 12 miles up versus satellite constellations of hundreds of miles away, not only do we reduce that signal latency for communications, but our sensor resolution goes up significantly. So being 30 to 50 times closer means the resolution of an image has gone up 900x to 2500x. So significant improvement there. Now, for Earth observation, that opens up a number of different avenues, everything from border patrol or security, infrastructure monitoring, even like biological population monitoring or just monitoring like vegetative states in some critical areas. So, yeah, Earth observation is a really big, broad category. Wildfire monitoring is another one that falls under that, where we have an MOU from the Washington Air National Guard because right now they have 3 people that fly in an airplane, right? They take off from the state of Washington, they jet down to California, they get about 20 minutes of data, and then they have to go home. So if we actually had something that could not only provide intel for the state of a wildfire, but also that persistence to be able to perhaps detect it a little bit earlier. The way our MOU signer described it was the first 6 hours of a wildfire largely determines whether they can put it out in 6 days or 6 weeks. So things like that can just really provide a significant benefit.
If you wanted to provide coverage across the United States, roughly how many turn systems would you need to deploy?
Now, this is where it gets really interesting. Since we're basically looking at being able to provide something like a complement or even a replacement to satellites, I always like to put the baseline compared to Starlink, right? It's no secret that in the absence of any sort of champion in the stratosphere, there has been a strong push towards satellite infrastructure, very low Earth orbit. Can we do the job? Even if it's not cell phones, like maybe we could just communicate with a dish in a fixed spot. So yes, I always like to benchmark it with Starlink. Starlink, to provide global coverage, has aspirations of deploying a 42,000 mega constellation orbit. Now, why so many? If you think about the Earth being 70% ocean, you don't get to pick where the satellites go. You just have to have it be homogeneously deployed across the entire planet. If you're talking about a solar powered aircraft that can reposition on demand, as an aircraft, we think about it as hover. That's an easy term to talk about. But when you think about a satellite, that's a geostationary capability, not just geostationary, but something that we can reposition. So we don't have to service the 70% of the planet that doesn't need it. So to answer your question, to be able to service the continent of the United States would only take a little bit north of 300 units.
As the system scales, how does it fit into the broader UAS ecosystem? Does it occupy its own layer in the atmosphere? Or is it more of a complement to existing systems like Starlink?
Yeah, absolutely. And I can answer that 2 ways. One would be physical proximity. So the nice thing about the stratosphere being 12 miles up or 60 to 65,000 feet is there aren't a lot of neighbors, right? We're above Class A airspace. General transportation is definitely below that. But we're not in space having to worry about the space debris from like all these mega constellations coming out of orbit. So the stratosphere is just a very nice, untapped domain, just location wise. Now, in terms of where it fits into the vertical stack, Yeah, absolutely. I would say terrestrial cell towers and satellites offer their own advantages. So it's nice to be able to think about how that would plug in at a larger scale. One of the things that I like to describe for the stratosphere is solar powered aircraft can really, if you think about autonomous driving, there's the term the last mile problem, right? Driving autonomously on the highway, super easy, it's very standardized, but getting into the driveway, that's really, really tough. So I like to say that the stratosphere can solve the last mile problem for the communications between terrestrial and satellite. So if we look at satellites, they're not encumbered by power requirements. The FCC isn't worried about like health effects. So they can broadcast as much power as they need. And if you're in space, we can also look at more up and coming emerging technologies like free space optical, being able to communicate with lasers. The problem is we still have to connect to the ground. And cell phones working on a fraction of a watt were never intended to communicate to something 600 miles away. So, how do we get those two things together? Or in the case of free space optical, if you want to transmit to a backhaul site, well, you have to worry about cloud coverage. Lasers don't like to go through clouds. So, if we actually had something that was in near space, now 12 miles up, we would still be able to operate with the higher RF signals that satellites are accustomed to. We'd still be above the weather to be able to connect it with those free space optical. But we're also close enough to be able to get that last mile problem to either the cell phone or the backhaul site.
Once deployed in the stratosphere, how does the system move? Is it relatively stationary, or can it reposition? And if so, how fast?
With low power aircraft, speed is not its claim to fame, but the larger systems we have looked at, not just, hey, we got to get from point A to point B, but more realistically, we need to be able to persist in some weather. So the largest scale system that we looked at, the one that had the 30-meter wingspan, that was specifically sized to be able to mitigate 120-mile-an-hour winds, which would give us 99.9% days aloft in the stratosphere.
You've described persistent flight as the last great aviation milestone. When did you first realize this problem might actually be solvable?
It was actually, I was still at NASA at the time, working on the Sikorsky Human Powered Helicopter Prize. So, for anybody that's not familiar with that, it was the legendary helicopter manufacturer put out like a $250,000 prize for anybody that could build a human powered helicopter, right? No engine, no fuel, just get 10 feet off the ground and hold it for a minute. People are not very good power plants. So that was a very, very difficult challenge that went unanswered for about 3 decades. So it was just a really, really interesting problem. And whereas most groups were looking at just making the rotors huge, I wanted to look at making them more efficient. And so my rotors, again, became really long, slender rotors. They were just very flexible, very flimsy. There wasn't any way to reinforce it. Everything mass wise went into reinforcing this flimsy structure, and that design just didn't close. But around the same time, I was seeing this proliferation of HAPS attempts, and everything just seemed to be stemming around long, skinny wings. How do we either mitigate the bending moment or put extra mass into the wing? And kind of the pivotal aha moment was, well, wait a minute, I kind of have the same problem with this rotor of long, skinny rotors. The only way I was thinking about reinforcing it for the contest was, well, maybe I could put a mass on the end and actually have it stiffen. But dead mass on a human powered helicopter doesn't close the design, right? So the pivot was, rather than dead weight, what if that was battery mass? And what if instead of a human powered helicopter, what if this was a solar powered persistent flight aircraft?
Would you say that breakthrough came from a moment of insight or serendipity? Or was it the result of a deliberate design process?
I would say having a dedicated, focused on one specific problem and coming up with at first what seemed to be a dead end at least opened up the imagination enough to see it as a solution in a completely different domain.
What's next for Devorto? What are the next steps in the evolution of Tern?
Yeah. So from the beginning, we've always adopted a spiral development philosophy rather than just going for that one aircraft and pretending that everything's going to be hunky dory out of the gate. We've always looked at it as spiral development. You address the most critical tasks at that moment, address the unknown unknowns, take the flight data you have, improve your analytic models, and then build the next biggest prototype. So for us personally, we're still working at a very small scale, but now we're getting the wingspan up to about 7 meters to start doing higher altitude flights. And the nice thing with that is with our MOU from the Air Force, when we were showing this technology progression of spiral development, their comment was, boy, right now the endurances that you're looking at would actually fly 20 times longer than a multi-rotor. If you build that sooner than later, we will buy it either for aerial wildfire monitoring or forward operating bases that need ISR and local comms. So a kind of another pivot was, yes, this vehicle was designed for the stratosphere for solar power consistent flight. But its claim to fame is aerodynamic efficiency. And so at each different milestone that we're progressing along, we're looking at different use cases that we'd be able to bring products to market. So right now, we're not only marching towards a stratosphere with solar cells and tethers, but we're also looking at what could we do with a Group 2 platform that could provide 10 hours endurance and say 300-mile range. What would that do for something like oil and gas pipeline inspection? And focus on, hey, is there a market that we could come to sooner than later?
From a defense perspective, does operating in the stratosphere provide advantages, perhaps making the system less accessible or more resilient compared to lower altitude platforms?
Yes, absolutely. Because the first thing that you would think is a slow flying, low power aircraft is going to be a really easy target, right? That's kind of just the off the cuff expectation. Where it gets interesting is that when you're in the stratosphere, if you actually look at the considerations for, well, how would you target that thing? What would you shoot up there? The list of options gets really, really small to the point where we're talking about something the size of like an ICBM is really about the only thing that would be able to realistically get to the stratosphere. So from some of the conversations we've had on the defense side, yeah, it might be an easy target. We'll find out because it's still low power. It's still low heat. So how much targeting would you need? But even if could be targeted, okay, well, if we're talking a million or $2 million aircraft, but you got to launch a 20 or $30 million missile to take it out, that's called winning the cost war.
With a payload capacity of up to around 250 pounds, that opens the door to a wide range of payloads.
Correct. And now, granted, that is of the spiral development. That's still probably 3 or 4 iterations down the road. But what we're looking to deploy in the stratosphere for Space Force, specifically for their AP&T payload, would be something that's comparable to what Zephyr is doing right now, 5 or 10 kilograms. So that will be out sooner than later.
Justin, before we close, is there anything that we missed that we should talk about?
Yeah, I would say just for the audience in general, I like to describe not just Tern as being yes, it is a solar power persistent flight aircraft. That's what we're going for. But in terms of the business model that we're looking at, we just want to be the aerial taxi. We want to remain payload agnostic. We just want to open up the realm of we can get sensors to previously inaccessible places, or we can provide endurances that open up new opportunities. So for the audience at large, I would actually kind of flip the script and say, what would you be able to do if you could fly for 20 times longer than multi-rotor? What would you be able to do if you could get your payload out of orbit and into the stratosphere?
That's it for episode 454 of the Drone Radio Show. I hope you enjoyed hearing from Justin Selfridge of Devorto. I want to thank Justin for taking the time to speak with me. If you want to learn more about Devorto or want to connect with Justin, visit spotterdevorto.io. If you like the Drone Radio Show, please subscribe, share the podcast, and leave a review on your favorite platform. And if you're able to support the show, you can donate at droneradioshow.com/donate. Thanks for listening. Your support truly means a lot, and I hope you'll tune in to future episodes of the Drone Radio Show podcast to hear how drones are being used for business, fun, and research. For the Drone Radio Show, I'm Randy Goers.
This has been the Drone Radio Show podcast. More information on today's show can be found on our website at www.droneradioshow.com. If you're using drone technology for business, fun, or research and would like to share your experience on the show, please visit our website and fill out a guest appearance application. And don't forget to follow us on your favorite social media channels.